Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. The moon seems motionless, forever presenting the same familiar face to Earth. For over 4 billion years, it has maintained this silent gaze in a phenomenon scientists call tidal locking. Tonight, we'll journey through the physics, the orbital mechanics, and the subtle forces that created this cosmic stillness, a tale of energy lost, gravity stretched, and time quietly unfolding. Part 1. Why do we always see the same side of the moon? Although it feels like the moon never spins, the reality is more subtle and fascinating. The moon does rotate, it simply does so at a pace perfectly matched to its orbit around our planet. This delicate synchronization is the result of billions of years of gravitational influence and friction, a natural consequence of motion and energy exchange. Data from NASA's Lunar Reconnaissance Orbiter confirms that the moon completes one rotation every 27.3 days, exactly the same time it takes to circle Earth. The result. From our vantage point, one hemisphere is always facing us, while the far side remains hidden. Early in its history, shortly after forming from the debris of a colossal collision between Earth and a protoplanet named Thea, the moon spun much faster, its days lasting only a few hours. But Earth's gravitational pull created tiny bulges in the moon, stretching it ever so slightly. These bulges generated tidal friction, an internal drag that gradually slowed the moon's rotation. Over time, the rotation matched the orbital period, locking the same face toward Earth in a state known as synchronous rotation. Mathematically, the moon's orbital speed is around 1 km per second, while its rotation rate is an astonishingly slow 0.037 degrees per hour, completing a full spin over a month. This precise balance isn't unique to Earth's moon. Many moons in the solar system, like Jupiter's Io or Saturn's Titan, are similarly tidally locked. Yet our moon stands out because of its size relative to Earth and the subtle precision of this alignment. Even what appears perfectly still is not entirely motionless. Through a phenomenon called libration, caused by the moon's elliptical orbit and slight tilt, about 59% of its surface can be glimpsed from Earth over time. This gentle wobble reminds us that even in apparent stillness, there is movement. Missions like NASA's Grail have mapped the moon's gravitational field, revealing variations that reflect tidal friction and internal deformation. The moon's crust, stress lines, and subtle fractures are enduring records of billions of years of gravitational stretching. As Dr. James Williams of NASA's JPL puts it, tidal locking is nature's way of trading rotation for stability. Imagine standing on the moon's near side. Earth hangs motionless in the sky, never rising or setting, while stars drift around it. On the far side, Earth never appears, an eternal reminder of this cosmic symmetry. The moon's tidal lock also shapes life on Earth. Its gravitational pull drives oceans, stabilizes our planet's axial tilt, and gradually slows Earth's rotation. This quiet partnership has helped make our world hospitable for life. The moon's stillness is not just a curiosity, it is a stabilizing force that has quietly shaped the rhythm of our planet for billions of years. Part 2. The invisible force that holds the moon. Nothing mystical locks the moon in place, only gravity, relentless and precise. For 4.5 billion years, Earth's pull has shaped the moon's rotation, slowing it until a delicate balance was reached. Newton's law of universal gravitation tells us that every mass attracts every other mass. For the Earth-Moon system, this force created bulges on the moon that didn't perfectly align with Earth's pull. This misalignment produced tidal friction, an internal resistance converting rotational energy into heat. Over millions of years, this friction acted like a cosmic brake. The torque from Earth's gravity gradually slowed the moon's spin until its rotation and orbital period perfectly matched. Today, the moon is in synchronous rotation, forever presenting one face to Earth. The forces at work were enormous. Early gravitational torque might have reached 10 superscript 1 Newton meters, heating the moon's interior. Though that heat has long dissipated, its geological signatures, crustal variations, fractures, and density differences remain as a record of this ancient process. Tidal dissipation models show that in its early history, the moon shed rotational energy at rates comparable to tens of gigawatts, akin to thousands of volcanoes working at once. Slowly, centimeter by centimeter, its spin aligned with its orbit, culminating in the perfectly synchronized rhythm we observe today. The moon's stillness is a visible record of this elegant cosmic dance, a slow, precise choreography shaped by time, friction, and gravity, reminding us that even what seems immobile can be the result of motion at its most refined. Part 3. The Moon's Slow Dance and the Invisible Hand of Gravity. Gravity works quietly, relentlessly, shaping worlds over billions of years. Dr. James O'Donoghue from JAXA describes tidal friction as the universe's slowest engine, patient, unyielding, and precise. In the Earth-Moon system, this invisible force has gradually transformed a freely spinning moon into a celestial partner moving in perfect harmony with its orbit. The secret lies in angular momentum conservation. The Earth and Moon share a total angular momentum, divided between the Moon's rotation and its orbit. As tidal friction inside the Moon dissipated energy, spin slowed while orbital motion subtly adjusted. Even today, the Moon drifts away from Earth at roughly 3.8 centimeters per year, measured by lasers bounced off reflectors left by Apollo astronauts. Though imperceptibly slow, over millions of years, this shift reshapes tides and the Moon's influence on Earth. Scientists liken it to a cosmic conversation. Earth tugs, the Moon resists, and over time, equilibrium emerges. This dynamic principle extends across the solar system. Jupiter's moon Io, for instance, endures extreme tidal stretching, generating more volcanic heat than any other body. Our moon experienced a gentler version, evidenced by the dark volcanic plains called mare basalts, which solidified 3 to 3.5 billion years ago, a record of heat once flowing beneath its crust. Tidal locking is not coincidence. It is the inevitable outcome of Newtonian physics. Given enough time, friction, and gravitational pull, massive bodies naturally settle into synchronized orbits. The Moon's center of mass is slightly offset, about 2 kilometers toward Earth, helping maintain this balance with millimeter-level precision. Subtle vibrations and oscillations cannot break the lock. The system is stable, sculpted over billions of years. NASA's Grail mission revealed the Moon's gravitational field in exquisite detail, confirming that ancient tidal heating shaped its interior and crust. Dr. Maria Zuber, Grail's principal investigator, explains, "The Moon's gravity field tells the story of a world shaped more by Earth than by itself." The Earth-Moon system is not two separate objects, it is a coupled dance, each influencing the other across space and time. Even now, this cosmic choreography continues. Earth's rotation slows under tidal friction, dissipating about 3.7 terawatts of energy yearly in the oceans. In billions of years, our planet too may become tidally locked, forever showing one face to the Moon. Gravity's invisible hand never tires. It converts motion into order, weaving stability from chaos. Part 4. A Moon once wild, now tamed. The serene Moon we see tonight belies its tumultuous past. Billions of years ago, it spun freely, molten and glowing, a world in constant motion. The giant impact hypothesis explains its fiery origin. Around 4.5 billion years ago, a Mars-sized body called Thea collided with Earth, launching debris into orbit. That material coalesced to form the newborn Moon, spinning rapidly, with a day lasting perhaps less than 10 hours. Its surface, molten from the impact, rippled under the relentless tug of Earth's gravity. This early rotation generated immense tidal friction within the Moon, converting kinetic energy into heat. The faster it spun, the more violently it flexed under Earth's pull, producing internal heating similar to the extreme volcanic activity seen today on Io. Unlike Io, however, the Moon's smaller mass could not sustain such eruptions. Instead, it cooled, stiffened, and gradually synchronized with its orbit. According to the Lunar and Planetary Institute, early Earth-Moon tidal interactions released energy on the order of 10 superscript 1 joules, enough to power modern civilization for millions of years. This energy reshaped the Moon's interior and crust, thickening it and making tidal friction less effective over time. By roughly 100 million years after its formation, the Moon's rotation had slowed enough to achieve near-perfect synchronization. One side now constantly faces Earth, the other remains in eternal shadow. The Moon's crust reflects this history. The near side, the one visible from Earth, is thinner, smoother, and dominated by vast basaltic plains, while the far side is thicker, heavily cratered, and rugged. These differences are not random. They are a fossil record of billions of years of gravitational stress. As Dr. Maria Zuber succinctly puts it, the Moon's shape is a memory of its motion, and that memory is measurable. Lunar laser reflectors confirm this stability. Over billions of years, the Moon wobbles only slightly, mere arc-seconds, echoes of a time when it spun freely. If we could witness that ancient sky, Earth would have raced across the heavens, rising and setting every few hours, while colossal tides reshaped both worlds. The crust itself may have cracked and reformed repeatedly, each cycle a testament to the power of gravity at work. In short, the Moon's stillness is not absolute. It is the result of eons of friction, energy exchange, and gravitational negotiation, a dynamic equilibrium that continues to evolve, imperceptibly, even today. The quiet moon in the night sky is not frozen, it is the product of a cosmic struggle, a dance of celestial mechanics that never truly ends. Part 4. The Moon's Outward Drift and the Secrets of its Hidden Side. NASA's 2023 high-resolution simulations reveal a fascinating story. The Moon's early spin and orbital path were intertwined. As its rotation slowed over billions of years, the Moon's orbit gradually expanded, a process that continues even today. Currently, the Moon drifts away at about 3.8 centimeters per year, a quiet echo of the same cosmic braking that once tamed its rapid spin. Each centimeter of drift represents rotational energy converted into orbital distance, a testament to the invisible, patient work of gravity. This phenomenon is not unique to our Moon. Across the solar system, tidal forces sculpt motion in predictable ways. Pluto and Charon, for instance, are mutually tidally locked, forever showing the same faces to one another. Mercury dances in a 3:2 spin-orbit resonance, rotating 3 times for every 2 orbits around the Sun. These examples confirm that given enough time, friction and gravity will always steer celestial bodies towards stable, synchronized motion. For the Earth's Moon, this perfect balance likely solidified 3 to 3.5 billion years ago. Since then, its rotation and orbit have been locked in near-perfect harmony. What appears as stillness is actually the outcome of precise equilibrium between 2 opposing forces, inertia and gravity. Inside the Moon, ancient scars remain. NASA's Grail mission revealed stress lines and density variations buried deep in the crust, fossils of tidal flexing that recorded a time when the Moon spun far more rapidly than today. Imagine a time-lapse of that transformation, a spinning top gradually slowing under invisible friction, wobbling, then stabilizing, until it aligns perfectly with its surroundings. The Moon underwent the same process, only over millions of years. Its rotational kinetic energy diminished, while its orbital angular momentum increased, preserving the total angular momentum of the Earth-Moon system. Chaos gave way to harmony. As Neil deGrasse Tyson observes, in space, everything moves toward balance, and balance is never truly still. The Moon's current orientation is the result of a long evolutionary process, guided entirely by physics. Once the mantle cooled and internal heat dissipated, its near side was set permanently toward Earth. Even today, any slight shift in rotation produces a restoring torque, maintaining alignment across billions of years. Despite impacts, moonquakes, and gradual changes, this configuration remains one of the most stable known in planetary mechanics. Yet, the Moon has a story beyond its familiar face. For thousands of years, humanity gazed only at its silver near side, oblivious to the hidden hemisphere. It was not until 1959 that the Soviet spacecraft Luna 3 revealed the far side of the Moon for the first time. The images, captured across 400,000 kilometers of space, stunned the world. This hidden hemisphere was rugged, cratered, and devoid of the smooth dark plains, the maria, that dominate the near side. The far side's crust is significantly thicker, averaging 15 kilometers more than the near side, according to NASA's Lunar Reconnaissance Orbiter, LRO. This thickness likely blocked magma from reaching the surface, leaving ancient impacts preserved as geological fossils. The near side, by contrast, with its thinner crust, allowed lava flows to fill basins and create the iconic dark plains we see from Earth. Chemical analyses reinforce these differences. The near side is rich in iron and titanium, while the far side contains lighter elements like aluminum and calcium. Researchers suggest that Earth's gravitational influence during the Moon's formation may have concentrated heat-producing elements on the near side, leaving the far side colder and more resistant to volcanic resurfacing. The far side is home to the South Pole, Aitken Basin, one of the largest known impact structures in the solar system. Spanning roughly 2,500 kilometers and plunging up to 8 kilometers deep, this colossal scar offers a glimpse into the Moon's inner layers. Data from Grail indicate that the impact may have exposed mantle material, a rare window into the Moon's composition. Modern high-resolution mapping by LRO, with cameras capable of resolving details smaller than a meter, has unveiled this hemisphere in unprecedented detail. The far side resembles a frozen storm, overlapping craters, long ejecta rays, jagged ridges, and valleys sculpted over billions of years. Some regions, like the Tsiolkovsky crater, hint at past volcanic activity, though these exceptions are rare. Lunar night temperatures here can plunge below -230 degrees Celsius (-382 degrees Fahrenheit), colder than anywhere on Earth, making it a world of shadow and silence. Dr. Mark Robinson, principal investigator of LRO's camera system, describes the far side as a geological museum, where every crater and ridge preserves the history of ancient collisions. Its unaltered surface serves as a time capsule, maintaining conditions from an era that the near side has long erased. The far side's frozen landscape reminds us that the Moon is not just a companion in the sky, it is a record of motion, impact, and gravitational sculpting stretching back to the dawn of the solar system. In 2019, China's Chang'e 4 spacecraft made history by landing softly on the far side of the Moon, in the von Karman crater within the South Pole, Aitken Basin. Its rover, Yutu-2, continues to relay data about the region's mineral makeup and subsurface structure. Analysis shows rocks rich in olivine and low-calcium pyroxene, likely originating from deep within the Moon's mantle, just as NASA scientists predicted decades earlier. Yet what captivates scientists most is not what the far side contains, but what it lacks. There are no vast seas, no smooth lava plains like Mare Imbrium or Mare Tranquillitatis, and none of the dark spots visible from Earth. In every sense, it is a different Moon. This difference has practical significance. Always facing away from Earth, the far side is shielded from terrestrial radio interference, making it one of the quietest locations in the solar system for radio astronomy. NASA and ESA have proposed future observatories here, aiming to capture faint signals from the first stars that formed after the Big Bang. But reaching this hemisphere is no small feat. Communication requires relay satellites, like China's Keiqiao, launched in 2018 to maintain a constant link with Chang'e 4. Humanity now has a stable connection to a once untouchable landscape. Standing there, the sky would be unlike anything seen from Earth. Earth itself would never rise, the stars would shine in unfiltered brilliance, and the Milky Way would stretch across the heavens with piercing clarity. Silence would dominate, broken only by the echo of footsteps across a surface untouched for billions of years. The far side's stark desolation is a direct consequence of tidal locking. Because it never faces Earth, it has endured the full force of meteoroid bombardment. In contrast, the near side benefits slightly from Earth's shielding, with debris that would otherwise strike absorbed or deflected. The result is a brutal symmetry. The side we see is calm, familiar, and mythic. The hidden hemisphere is raw, scarred, and ancient. As Neil deGrasse Tyson once said, the far side of the Moon is not dark. It's just unseen. And unseen, it continues to shape our understanding of planetary evolution under the quiet but relentless influence of gravity. Even now, the gravitational relationship between Earth and Moon remains active. The Moon drifts away from Earth at roughly 3.8 centimeters per year, about 1.5 inches annually. Measured with astonishing precision using laser reflectors left by the Apollo missions, this slow migration is a direct consequence of tidal friction, the same force that first locked the Moon's rotation. Tidal friction works quietly but relentlessly. Earth's gravity raises tiny bulges on the Moon, just as the Moon raises tides in our oceans. Because neither body rotates perfectly in sync with these bulges, torque is generated, transferring energy from rotation to orbit. In this cosmic exchange, Earth loses a fraction of its spin while the Moon gains orbital energy, slowly drifting farther away. Modern measurements, using facilities like the Apache Point Observatory, can detect these changes down to mere millimeters. The data align perfectly with Newtonian mechanics and Kepler's laws, confirming that this gravitational handshake has been ongoing for billions of years. Visualize it: Earth's oceans act as enormous, mobile brakes. The moon's pull creates tidal bulges that are slightly ahead of its position due to Earth's faster rotation. These bulges tug back on the moon, giving it extra momentum in orbit. Simultaneously, this interaction drags on Earth's rotation, lengthening our days by about 1.7 milliseconds per century. Over hundreds of millions of years, a day on Earth will grow beyond 25 hours. This system remains dynamic, even though the moon's rotation is already synchronized. The forces that first froze the moon are still subtly adjusting the orbit, continuing to shape both bodies over geological time. Scientists describe this as gravitational aging. As the moon drifts outward, its orbital speed slows, tidal forces weaken, and the pace of change gradually diminishes. Eventually, billions of years from now, Earth itself will become tidally locked to the moon. One hemisphere of our planet will eternally face the moon, while the other will never glimpse it again. Until that distant moment, every ocean wave, every tide, contributes infinitesimally to the moon's outward journey. In fact, roughly 3.7 terawatts of energy, nearly the total power consumption of humanity, is dissipated as heat in Earth's oceans each year through tidal friction. That energy does not disappear, it transforms into orbital momentum, steadily nudging the moon away from us. So, is Earth still killing the moon's spin? Not exactly. The moon's rotation is already locked in perfect harmony. What continues is a subtle, ongoing dance of energy transfer, keeping the Earth-Moon system in equilibrium. The moon's face remains fixed toward us, a testament to billions of years of cosmic negotiation. Fossilized tidal records in ancient rocks further confirm this story. Around 400 million years ago, days lasted 21.9 hours, and the year had roughly 420 days. These patterns match modern laser data, proving that the moon's slow drift outward has been steady for hundreds of millions of years. The physics is simple. The consequences, however, are immense. Every wave, every tide, every subtle shift in orbital energy carries the imprint of a gravitational dance billions of years in the making. A dance that continues silently above us, shaping the moon, Earth, and the story of life itself. Tidal forces are among the universe's most powerful engines of energy transformation. They shape galaxies, stretch and tear comets apart, and dictate the spin of planets and moons. On Earth, they regulate oceans, stabilize the climate, and may even have guided the evolution of coastal life. That same invisible pull that raises our tides is the force that sculpted the moon's orbit, a conversation across 384,400 kilometers, ongoing and unbroken. As Dr. Neil deGrasse Tyson eloquently put it, tides are proof that even across the void, Earth and Moon are still touching. This is not metaphor, but physics. Earth's gravity deforms the moon tugs on our oceans. Every oscillation, every microscopic shift, is part of a billions of years old feedback loop. Though the moon appears still, it exists in a living system, a dynamic equilibrium that is stable precisely because it constantly adjusts. But imagine, just for a moment, that this balance were broken. What if tonight, some colossal impact or cosmic accident jolted the moon, setting it spinning freely once again? This isn't pure fantasy. Astrophysicists have modeled such scenarios, and the consequences would ripple across the solar system in ways both mesmerizing and catastrophic. The first effects would be felt here on Earth. Our tides, currently governed by the moon's steady pull, would become unpredictable. High tides could surge where they should recede, low tides vanish where they should appear. Ocean currents, temperature gradients, and wind circulation, all finely tuned by lunar gravity, would fluctuate erratically. NASA scientists remind us that tides are planetary, not just oceanic. Disturb the moon's rhythm, and Earth's energy flows are disrupted. The moon itself would suffer. Its crust, mantle, and core have settled into billions of years of tidal equilibrium. A sudden spin would stress its interior violently. Fractures could open, releasing stored energy, while the thick far side might crack more dramatically than the near side. Even a 10% increase in rotation could generate massive seismic waves, shaking the moon from pole to pole. Apollo-era seismometers already recorded quakes caused by tidal flexing. Renewed rotation would magnify these tremors, shifting dust and regolith across cratered slopes. The most profound effects, however, would unfold on Earth. The moon stabilizes our planet's axial tilt at roughly 23.5 degrees, giving us predictable seasons and moderate climate cycles. A spinning moon would weaken this gravitational tether. Over millennia, Earth's axis could drift chaotically between 10 degrees and 45 degrees, reshaping sunlight distribution, melting and refreezing polar ice unpredictably, turning deserts into fertile lands and tropics into frozen plains. The steady rhythm that governs days, nights, and seasons would fracture. The consequences extend further. Lunar spin affects the moon's mass distribution, or mass quadrupole moment, and even minor changes could perturb its orbit, making it slightly more elliptical. Night illumination and tidal strength would fluctuate cyclically. Orbital instability grows slowly, but inexorably. In short, if the moon began spinning freely again, we would not simply lose the familiar face in the sky. We would lose part of the cosmic framework that keeps Earth habitable. Ocean tides would destabilize, climates would swing unpredictably, and the rhythms of countless species, tuned to the moon's cycle, would be disrupted. Dr. Tyson encapsulates it perfectly. Without the moon, Earth would be a restless planet, wobbling, swaying, never sure of its balance. The moon's stillness is not mere aesthetics. It is structural, stabilizing, essential. The tidal lock is not a limitation, it is a cosmic safeguard, preserving the delicate dance that sustains life on our planet. We often call the moon still, but in truth, it never truly is. Even as it hangs motionless in our night sky, it rocks, tilts, and breathes in subtle, rhythmic motions. This delicate dance is known as libration, and it allows us to glimpse 59% of the lunar surface from Earth, not just half. To the naked eye, the moon appears frozen, its face always turned toward us. Yet NASA's precise measurements reveal that it shifts ever so slightly, moving back and forth, up and down, as it orbits Earth. These tiny oscillations arise from its elliptical orbit, axial tilt, and orbital geometry, giving the impression of a gentle nodding or swaying, a moon that seems to breathe. There are three main types of these motions: libration in longitude, libration in latitude, and diurnal libration. Together, they transform the moon's apparent stillness into a subtle, complex ballet dictated by the same laws Johannes Kepler and Isaac Newton described centuries ago. Libration in longitude occurs because the moon's orbit is elliptical. It speeds up near Earth, perigee, and slows down when farther away, apogee, while its rotation remains nearly constant. This mismatch lets us peak slightly around the edges, producing about 16 degrees of side-to-side rocking. Libration in latitude arises from the moon's 6.7 degrees axial tilt relative to its orbital plane. As it orbits, we alternately see slightly over the North Pole and under the South Pole, revealing an additional 6 degrees of lunar territory over a month. Diurnal libration is caused by our changing perspective on Earth. As our planet rotates, the moon is viewed from slightly different angles at sunrise and sunset, producing a tiny parallax shift of roughly 1 degree. Combine these effects, and the illusion of perfect stillness dissolves. The moon's motion, though imperceptible to us, is constant and measurable. Laser altimeters, radio tracking, and stereoscopic imaging, like NASA's Lunar Reconnaissance Orbiter, detect height changes as small as 10 centimeters, mapping the moon's breathing in astonishing detail. Even the moon's internal structure participates. Mascons, high-density regions left by ancient impacts, subtly distort the gravitational field, altering spin and oscillations over long timescales. Its partially molten core interacts with the solid mantle, causing minute changes in vibration patterns. In effect, the moon is alive with motion, from crust to core, transmitting secrets of its formation, evolution, and interior to scientists who know how to listen. Dr. Richard Gross of NASA's Jet Propulsion Laboratory describes it beautifully. The moon's motion is a mirror. It reflects not only gravity's pull but the history of its interior. Accelerate time, and you would see it pulse and sway like a slow pendulum, its orbit widening, poles nodding, surface flexing, a dance invisible to our human eyes, yet critical to maintaining Earth-Moon equilibrium. Even in apparent silence, the system fine-tunes itself. Oscillations, vibrations, and micro-adjustments allow gravity, rotation, mass, and orbit to work in perfect harmony. Every tilt, sway, and rhythmic inch keeps our world stable. The moon's stillness is not weakness, it is precision, endurance, and balance, the result of billions of years of cosmic negotiation. And yet, this subtle motion raises a deeper question. How did such perfect synchronization begin? Was it a random accident of nature, or something far rarer, a celestial outcome so precise that it challenges the very notion of coincidence? Part 8. How did this perfect synchrony begin? In a solar system filled with chaos, worlds spinning at different rates, colliding, drifting, breaking apart, Earth and its moon somehow ended up locked in a flawless gravitational rhythm. How did it happen? Pure chance? Or did the laws of motion make this balance inevitable? To understand, we must look beyond Earth. Surprisingly, tidal locking is common across the solar system. Of the 290+ known moons, many, Io, Europa, Ganymede, Titan, Enceladus, Rhea, and Charon, show one face to their planets forever. Gravity's persistence makes tidal locking natural. Yet our moon is unique. Its size and mass ratio to Earth is enormous. 27% of Earth's diameter and 1.2% of its mass. By comparison, Jupiter's Ganymede is only 4% of Jupiter's diameter. This unusual proportion allowed efficient exchange of angular momentum, locking the two bodies into synchronization faster than smaller moons could. Dr. James Williams of NASA's JPL explains it plainly. The Earth-Moon pair is locked not because the mechanism is special, but because the proportion is special. Early in the solar system, tidal locking was common but varied. Mercury spins 3 times for every 2 orbits around the Sun, a 3:2 resonance. Pluto and Charon are fully locked, rotating as a frozen duet. Earth and Moon occupy a delicate in-between state. One body spinning faster, the other slowly evolving, creating a balance that stabilizes our days, tides, and axial tilt. Astronomers run simulations, plugging in random masses, distances, and rotation speeds. In most cases, the Moon either crashes into its planet or drifts away. Only a narrow range produces a long-term stable tidal lock, and Earth's moon falls perfectly within it. Planetary scientists describe it as a natural coincidence amplified by scale. The moon's formation from a giant impact gave it exact mass and distance to reach synchronization in just a few billion years. Too small or too distant, and the lock wouldn't have happened. Instead, the forces aligned, creating a gravitational resonance so precise it seems deliberate. Dr. Maria Zuba of MIT and the Grail mission notes, the moon's orbit is a fossil of formation. Its current motion tells the story of how chance settled into order. Mathematically, this equilibrium is captured by the tidal torque equation. The gravitational potential of Earth interacts with the moon's deformation. Tidal bulges align, torque transfers energy, and the moon's rotation slows while its orbit expands. The energy lost, once tens of terawatts, is now recorded as tiny tidal shifts and the moon's 3.8 cm per year drift, measured by Apollo laser reflectors. Each centimeter is a cosmic ledger of energy exchanged. The lock also required the moon's thermal evolution. Its interior had to cool and solidify just enough to support the tidal bulge. NASA's Grail and LRO data show the crust thickened unevenly, reinforcing the asymmetry that keeps one side facing Earth. Gravity shaped the crust, and the crust stabilized gravity in return. This is why many scientists now consider the Earth-Moon pair a gravitationally coupled binary, a system whose precision stands apart in the solar system. Even Pluto and Charon, the closest analog, are smaller, colder, and slower. Earth's moon is dynamic, vibrant, tides flow, energy moves, balance persists. Statistically, this configuration is rare, yet given enough time, nature makes it inevitable. The universe allowed billions of chaotic possibilities to unfold, and one of them produced a moon perfectly tuned to stabilize Earth. Dr. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." Yet, the Earth-Moon lock does make sense. A cosmic balance emerging naturally from chaos, where gravity and time shaped order from randomness. The synchronization is self-stabilizing. Any minor disturbance, a small impact or internal shift, creates restoring torque, returning the moon to alignment. Gravity has written its own rule of balance, and the Earth-Moon system obeys it perfectly. Dr. Jack Liesauer describes it as nature finding harmony in randomness. And yet, this perfect lock prompts a deeper question. How did the story begin? What violent event created this delicate partnership that now defines our sky? Part 9. Could the moon's stillness hide evidence of its violent origin? The moon looks calm, but it was born from chaos. Every crater, ridge, and grain of dust is a fossil of impact, a memory of heat and violence. At its origin lies one of the most cataclysmic events in Earth's history, the Thea impact. A collision so powerful it nearly destroyed our planet, but instead created our quietest companion, a moon forged in fire, flung into orbit, and slowly tamed by gravity into the steady rhythm we see today. Around 4.5 billion years ago, the early solar system was a battlefield. Planets were newborn, molten, unstable, and surrounded by debris from the birth of the sun. Earth itself was barely recognizable. Smaller, hotter, still forming. Then came Thea, a protoplanet roughly the size of Mars, on a tilted orbit that intersected Earth's path. Simulations from NASA's Ames Research Center and Harvard's Origins of Life Initiative suggest the collision struck at a shallow angle, at about 9 kilometers per second, fast enough to melt crust, vaporize rock, and fuse the two worlds in a blinding instant. The energy released, 10 superscript 2 joules, reshaped both bodies. Trillions of tons of molten rock were ejected into orbit. Some escaped, but most remained bound by gravity, forming a glowing disk of vaporized silicate and metal around Earth. Over a few thousand years, that disk cooled and coalesced into the moon. NASA's Lunar and Planetary Institute calls it the greatest recycling event in planetary history. The moon is, in a sense, made of Earth, and Earth has carried a missing piece of itself ever since. Dr. Robin Canup summarized it perfectly. The moon is what happens when a planet tries to heal. But that healing was violent. After the impact, both Earth and the newborn moon were red hot, wrapped in thick clouds of rock vapor. As they cooled, their mutual gravity began to reshape each other. Earth, spinning far faster than today, caused the newborn moon to orbit just 22,000 kilometers from the surface, a distance so close it would have appeared enormous in the sky. At that proximity, tidal forces were immense. Earth's gravity stretched the young moon, creating tidal bulges that deformed its molten crust. Meanwhile, the moon tugged back, slowing Earth's rotation. This tug-of-war transferred angular momentum from Earth's spin to the moon's orbit, pushing it outward and gradually stabilizing its rotation. From chaos came rhythm. From fire came synchrony. The mechanics are exact. Conservation of angular momentum demanded that as Earth slowed, the moon's orbit expanded. What began as a searing molten aftermath evolved into a double-world system, each shaping the other's motion until equilibrium was reached. Modern evidence supports this. Apollo samples show nearly identical isotopic ratios of oxygen 16 and oxygen 18 in Earth and Moon, confirming their shared origin. The Moon isn't a captured asteroid, it's Earth's own material, reforged by impact. In 2022, NASA's Goddard team proposed an even more dramatic model, the Synestia hypothesis. The collision created a massive, spinning, donut-shaped cloud of molten rock, inside which the moon condensed, partially embedded in Earth's extended atmosphere. Dr. Sarah Stewart explains, the moon didn't form next to Earth. It formed within it. The boundary between them was blurred for thousands of years. Viewed this way, the moon's stillness today is extraordinary. A system born in fire and chaos has cooled over billions of years into one of the most stable orbits in the solar system. The Earth-Moon pair achieved a gravitational partnership so precise it maintains near-perfect balance. Seismic data from Apollo experiments revealed deep fractures, remnants of early tidal heating, and NASA's Grail mission mapped density anomalies in the lunar crust, confirming that the moon still bears the scars of its violent formation. The near side's thinner crust and the far side's thicker crust likely date back to Thea. Earth's still molten surface radiated heat toward the near side, influencing how its crust solidified, a subtle difference locked in for billions of years. This connection between destruction and harmony is not unique. Planetary systems form from collapsing gas clouds. Stars emerge from turbulence. Galaxies stabilize after collisions. The Earth-Moon system is one local example of a universal pattern, energy organizing itself through gravity and time. If we could replay the Thea impact in slow motion, it would look familiar. Chaos, compression, expansion, equilibrium. The same pattern governs stars, galaxies, and even molecular bonds. Energy seeks balance, and when it finds it, stillness emerges. The moon's calm face isn't hiding its origin, it is its origin transformed. Every orbit, wobble, and tidal pulse carries the memory of that first collision. As Dr. Neil deGrasse Tyson said, the moon is a witness not of peace, but of the moment when Earth learned how to keep time. Through the moon, we trace the history of balance itself. From that single violent act came our satellite, our tides, our stable climate, and the conditions that make Earth habitable. Tonight, when you look at the moon's serene glow, you aren't seeing emptiness. You're witnessing the fossil light of a catastrophe long cooled, a perfection of balance forged from unimaginable energy. Part 10. The Moon's Eternal Dance. One day on Earth will one day last an entire month. The oceans will no longer rise and fall, and in the silent sky above, the moon will hover motionless, forever fixed above one side of our planet. This is not science fiction. It is the final stage of a slow, ongoing process that began the moment the moon was born. Right now, the moon drifts away from Earth at about 3.8 centimeters per year, a distance meticulously tracked by NASA's lunar laser ranging experiments, which have reflected light from the Apollo mirrors for over 50 years. This gradual retreat is driven by tidal friction, the same invisible mechanism that once locked the moon's rotation, but the process is far from finished. Energy is still being exchanged between Earth's spin and the moon's orbit, quietly, relentlessly, with every tide that rolls across our planet. As Earth rotates, its tidal bulges, slightly misaligned with the moon's position, pull the moon forward, adding angular momentum and pushing it outward. Meanwhile, Earth slows. Conservation of angular momentum demands balance. What the moon gains, Earth must lose. Dr. James O'Donoghue, a planetary scientist formerly with NASA, explains, "It's like a cosmic seesaw. Earth gives away rotation. The moon takes distance. Both are heading toward equilibrium. That equilibrium has a name: mutual tidal locking. When it occurs, Earth's day will match the moon's orbital period. One hemisphere will always face the moon, while the other will never see it again. NASA models estimate this could happen in roughly 50 billion years, long after the sun becomes a red giant. Yet, as a gravitational system, the Earth-Moon pair will slowly march toward that locked state, unless disturbed by other cosmic forces. At that distant time, one day on Earth will stretch to match the moon's month-long orbit. Tides will stop flowing. Oceans will settle. The energy exchange will cease as the torque driving it, the offset between Earth's rotation and the moon's orbit, vanishes. Everything will slow to a standstill. Even balance in space, however, is not eternal. As the sun evolves, its increasing radiation and mass loss will subtly alter Earth's orbit and spin. Solar tides may slightly nudge the system, but escape is virtually impossible. To break free, the moon would need to exceed Earth's escape velocity, about 5,800 kilometers per hour. No known natural force within this system could achieve that. Instead, the more probable future is a kind of eternal companionship, a frozen dance. Over billions of years, the moon will circle farther and farther away until it settles into mutual lock with a slowly rotating Earth. From the moon, Earth will stop rising and setting, frozen as a blue and white half-sphere in the sky. From Earth, one hemisphere will always see the moon overhead, the other never at all. The familiar rhythms of waxing and waning, of full moons and crescents, will end. One of the oldest clocks in the sky will pause. Dr. Neil deGrasse Tyson describes this future as a universe settling into stillness. Not death, but equilibrium. That stillness is not lifeless. It is the natural conclusion of motion, a balance reached after a long exchange of energy between two celestial bodies. From galaxies to atoms, every system in the cosmos moves toward it. When that day arrives, if any observers remain on Earth, they will see a moon locked forever above the same horizon. The craters, the Maria, the face we know so well, frozen in perfect alignment. It will be the ultimate calm, the end of tides, the end of spin, the end of motion between two worlds. And perhaps that calm will reveal something profound. What looks motionless is simply the completion of motion perfected. The moon's stillness is not absence, it is equilibrium. Yes, the moon will stop facing us, but only when Earth itself has slowed enough to face it back. Two worlds, locked together, unmoving, orbiting as one. A day will last as long as a month. The tides will sleep. The sky will stand still. And if tonight's journey has brought you even a small moment of calm, I am deeply grateful that you have shared it with me. A gentle like or a soft tap on subscribe isn't just support. It helps me continue crafting these night voyages into science and silence. I'd also love to know where you're listening from. Which corner of this turning world holds your night? Your words, whether short or long, are like tiny lights in this vast universe, and I read every one with care. Until we meet again under another quiet sky, sleep well, and dream gently of the world still spinning above us.